Welcome to Chapter 4 and Lebesgue integration. I'm going to start with 4.1, a pretty brief review of Riemann integration. We really thoroughly looked at Riemann integration when we looked at the Riemann-Lebesgue supplemental material. So all I want to accomplish in section 4.1 is to define the Riemann integral in a specific way that foreshadows how we're going to define Lebesgue integration. Remember, Lebesgue is going to rip Riemann off in the sense that it's still going to be base times height ideas, like in Riemann sums, where the bases are now measures of sets instead of intervals, and the heights are determined somehow by function values, just like Riemann would do. So we'll define the Riemann integral in a couple of equivalent ways. One of these you may have seen in your senior level analysis class. Probably the integration you would do would be in analysis 2. And the second way we'll describe it really is just to inspire the way we'll approach Lebesgue integration. So we'll start with a partition of the x-axis. A partition of the interval AB is a set x sub 0 through x sub n, a collection of points from the interval from A to B, where the first x sub 0 equals the left-hand endpoint A, the last, the x sub n, equals the right-hand endpoint B, and the index indicates the order of the points as they're laid out along the real line, and the points are distinct. The x sub 0 through x sub n are distinct as well. So we'll define something called a Darboux sum. This is really basically the same thing you did in Calculus 1 when you define Riemann sums. Touch more complicated in terms of how the heights are determined. So let f be a bounded function on the interval from A to B. Riemann always starts with bounded functions on closed and bounded sets. For P, a partition of the interval AB, define the lower and upper Darboux sums for function f with respect to partition P as lower Darboux sum of f with respect to P is a sum from I equals 1 to n of lowercase m sub I times x sub I minus x sub I minus 1. And upper Darboux sum of f with respect to partition P is a sum from 1 to n of capital M sub I times x sub I minus x sub I minus 1, where these m sub i's, lowercase and capital, are defined in terms of sups and nths. We'll define lowercase m sub I to be the nth of the function values when we input x between x minus 1, x sub I minus 1, and x sub I. We'll define capital M sub I to be the supremum of f of x when x ranges between x sub I minus 1 and x sub I. These sups and nths exist as finite numbers because we're dealing with a bounded function. So every set has a least upper bound and a greatest lower bound. So both of these are defined. Notice this is out of the Royden and Fitzpatrick book. The endpoints are excluded altogether. So the behavior at x sub I minus 1 and x sub I isn't part of the story in the choice of either lowercase m sub I or uppercase m sub I. We'll do it somewhat differently when we look at the second approach. All right, so we've got upper and lower, basically Riemann sums. We've called them upper and lower Darboux sums. Let f be a bounded function on the interval from A to B. We'll define lower and upper Riemann integrals of f over that interval as follows. First, we're going to use now and then this ugly r in parentheses to indicate these are Riemann integrals because we're saving the nice notation for Lebesgue integration. But we'll briefly encounter Riemann integrals. The Riemann integral, lower Riemann integral of function f on the interval from A to B is defined as the sup over all partitions of the interval AB of lower Darboux sums of f with respect to P. So you think, well, the lower Darboux sums, they're too little. We use like infima function values to determine heights there. So these are going to be too little. Well, then take yourself a sup over the things that are too little. Down here, for the upper Riemann integral from a to b of f is defined to be the nth of the upper Darboux sums of f with respect to p, where p ranges over all partitions. The nth and sup are taken over all partitions of the interval ab. All right. Well, you think of the upper Darboux sums as being like too big because you based those on suprema of function values. So, well, if they're too big, then let's shrink them. So kind of similar to what we did in developing outer measure and inner measure, if we explored that. We've taken the things that are too little and swelled them up, and we've taken the things that are too big and shrunk them down. So with nths and sups, everything is bounded. So we don't have concerns with these sups and nths being infinite for bounded functions. So there's a definition of lower and upper Riemann integral. And we could define a function to be Riemann integrable if these things are equal, if the lower Riemann integral equals the upper Riemann integral. So when those two things are equal, the function f is said to be Riemann integrable, and the common value is the value of that integral. All right. Well, I'm content with this idea somewhat. Let's tweak it a little bit, though, and try to shift it into a format that inspires the way we'll approach Lebesgue integration. We'll approach Lebesgue integration by approximating functions with other functions. So what I want to do is I want to change these upper and lower Darboux sum things. I want to change those into integrals of a particular kind of function. Now, in the Kirkwood book, An Introduction to Analysis, the book I use in senior level analysis, it's been a while since I've taught it, but it stands the test of time. This is the same definitions they have. They use the term Riemann sum instead of Darboux sum. And the one modification really is they define the m sub I, lowercase and capital M sub I, over the closed interval from x sub I minus 1 to x sub I. Up there in the Darboux sums, they eliminated the endpoints. Down here, we're including the endpoints. I have some notes posted online. It goes through that in some detail. So that's sort of a standard senior analysis way of encountering this. I want to try something a little bit different. Let's first define a step function. A real valued function, psi, defined on the interval AB, is a step function if there's a partition of the interval AB and numbers C1 through C sub n, such that the function psi takes on the value C sub I on the ith subinterval determined by that partition. Okay, so it reminds me a little bit of simple functions. Well, it is a simple function where the sets on which the function is constant are intervals or unions of intervals. But these are the kinds of functions you deal with when making Riemann sums in Calculus 1. So this sum stuff can be replaced in terms of these ideas of step functions. But step functions are continuous on little subintervals. That's the reason they're called step functions, because they look like a sequence of steps going up and down or all over the place, depending on the C's. So constant on little subintervals. For a step function psi, notice that the lower Darboux sum of psi with respect to partition P, where P is the partition that determines that step function, is simply a sum from I equals 1 to n of the value C sub I times x sub I minus x sub I minus 1. Of course, these are the lengths of those little subintervals, and C sub I, well, that's the value of psi on that little subinterval. It's the sup, it's the nth, they're the same because that function's constant on those subintervals. So the lower Darboux sum and the upper Darboux sum are exactly the same over those subintervals. Now that means, since we defined Riemann integrals in terms of upper and lower Darboux sums, and we always get the same thing, that means the Riemann integral of this step function psi from A to B will simply be that sum. So we've picked a very elementary kind of function, a step function, and integrals of that step function are simply these sums. So we're replacing sums with integrals of step functions. That means we can take what we started with in terms of defining lower and upper Riemann integrals and replace the fact that we were looking at, what did we have here? Lower Darboux sums. We're replacing those lower Darboux sums with step functions, integrals of step functions, Riemann integrals of step functions. So we're taking a Riemann integral from a to b of shifted the variable to phi, where phi is a step function and phi is less than or equal to f. So having phi less than or equal to f guarantees we're dealing with values less than function values. So that inf stuff is replaced with this. But we're replacing the Darboux sums with integrals of step functions in both cases. In this case, we're taking the step functions phi that are greater than or equal to f, because here we wanted upper. We wanted upper Darboux sums, and we took imps of upper and sups of lower, was the pattern we had before. So we simply replaced the Darboux sum stuff with integrals of step functions. All right, that's how we're going to approach Lebesgue integration. We'll start with a basic class of functions. That basic class of functions will be simple functions. And simple functions are to Lebesgue integration kind of what step functions are to Riemann integration. I'll use simple functions sort of to define what a Lebesgue sum is versus a Riemann sum. Same idea. I'm still thinking base times height, quote unquote height. I worry about the function values being negative. The word height is a distance and it couldn't be negative in a strict use of the term. Well, the function values can be. So when I say base times height, I'm talking not necessarily about area, but signed area or quote unquote area. You know, the problem you get with negative functions and area interpretations out of integrals from calculus 1, you know that. So we're doing the same thing Riemann does, except we're introducing classes of functions to produce the Riemann sums. And then we'll take sups and imps over elements of that class of functions. Similar to what we did here. So instead of talking about things in terms of sups and imps of Darboux sums, we'll talk about things in sups and imps of integrals of step functions. And here's the definition, if you like, if you want to start from scratch. Here's the definition of the Riemann integral for simple function psi. So we'll do that kind of thing in Lebesgue. We'll start with one layer of functions, the simple functions, and then we'll move on to progressive layers of functions. With Riemann, there's step functions, and then there's functions that can be Riemann integrated. With Lebesgue, there's simple functions. Beyond simple functions, there will be bounded functions on sets of bounded measure. All that bounded stuff, we're trying to avoid some kind of divergence issues. That'll be the second layer of functions we deal with. We'll use that layer of functions to deal with non-negative functions. And then we'll use that layer of functions to deal ultimately simply with measurable functions. And unless we run across infinity minus infinity in some of this stuff, we'll have to avoid that. We're good to go. We will have the Lebesgue integral defined for all measurable functions, provided we avoid some infinity minus infinity meaningless nonsense. And it'll be built up in layers, very, very analogous to what we've done in defining the Riemann integral in terms of Riemann integrals of step functions. So that's the real takeaway of this little mini section there. So next we'll move on to section 4.2, and we'll start this Lebesgue integration project. I'll see you in 4.2.